Grounding and bonding are crucial for electrical safety. The National Electrical Code, or NEC, mandates that all electrical systems must be grounded. At the meter or farm panel, a ground rod must be driven. This provides a low impedance path to earth for fault currents and lightning strikes. The ground rod should be a minimum of 8 feet long and driven into conductive soil. Now, considering the house panel, if the house is within 30 feet of the meter or farm panel, a separate ground rod is not strictly required at the house. However, the ground wire from the meter or farm panel must be extended to the house panel and connected to the ground bar. For the garage panel, a similar rule applies. If the garage is also within 30 feet of the meter or farm panel, a separate ground rod may not be required at the garage. The ground wire from the meter or farm panel must be extended to the garage panel and connected to the ground bar. Moving on to bonding, the neutral and ground conductor must be bonded at the meter or farm panel. This establishes a common grounding electrode system. At the house panel and garage panel, if present, the neutral and ground conductor must also be bonded. Furthermore, the equipment grounding conductor, or EG, of any feeders going to the house or garage must be connected to the ground bar of the respective panel. The primary purpose of grounding is to provide a low resistance path for fault currents to flow to earth, protecting people and equipment. Bonding the neutral and ground conductors ensures that there is not a potential difference between the two systems, minimizing the risk of electrical shock. The EGC provides a path for ground fault currents to flow safely back to the source, preventing damage to equipment and ensuring proper operation of overcurrent protection devices. Now, let's consider a scenario where the first means of disconnect is at the pole and the service is within 30 feet of the house or garage. Even in this case, a ground rod should be driven at the house and garage. This ensures that there is a proper grounding electrode system at each location, providing safety and protecting the electrical equipment. The neutral and ground conductors must be bonded at all panels to maintain a common grounding system. The NEC outlines specific requirements for grounding electrode systems. Section 250.50 covers grounding electrode systems, stating that all grounding electrodes described in 250.52 that are present at each building or structure served must be bonded together to form the grounding electrode system. This creates a low impedance path for ground fault current. Section 250.52 details acceptable grounding electrodes, including metal and groundwater pipes, metal and ground support structures, concrete encased electrodes, and ground rods and pipes. A ground rod electrode must be at least 8 feet long and, per 250.53, must be installed such that at least 8 feet of the electrode is in contact with the soil. Supplemental electrodes are often required. For example, 250.53. 8.2 states that a single ground rod electrode must be supplemented by an additional electrode of a type specified in 250.52 or 250.54. This ensures redundancy and a lower overall ground impedance. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the ungrounded service entrance conductors. For example, if the service entrance conductors are 2/0 American wire gauge, or AUG, copper, the grounding electrode conductor must be at least 4 AWG copper. Bonding is equally critical. Bonding ensures that all metallic parts within an electrical system are at the same electrical potential, minimizing shock hazards. Section 250.92 discusses bonding of metal enclosures containing service conductors. Metallic enclosures such as service conduit and meter cans must be bonded to the grounded conductor or grounding electrode conductor. This prevents voltage from developing on these enclosures during a fault. Section 250.94 covers bonding of other metal parts. Exposed structural metal that is interconnected to form a metal building frame and is not intentionally used as an equipment grounding conductor must be bonded to the grounding electrode system. This prevents these metal parts from becoming energized during a fault. Equipment grounding conductors, or EGs, play a vital role in clearing ground faults. EGC provide a low impedance path for fault current to return to the source, allowing the overcurrent protective devices, such as circuit breakers and fuses, to quickly trip and de-energize the circuit. Section 250.118 lists acceptable types of equipment: grounding conductors, including copper or aluminum conductors, rigid metal conduit, electrical metallic tubing, and flexible metal conduit under certain conditions. The size of the EGC is determined by NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. For example, if the overcurrent device is rated at 20 amps, the EGC must be at least 12 AWG copper. Ground fault circuit interrupters, or GFCIs, provide an additional layer of protection. GFCIs are designed to detect small imbalances in current between the hot and neutral conductors, indicating a ground fault. When a ground fault is detected, the GFCI quickly trips the circuit, preventing electrical shock. GFCIs are required in many locations, including bathrooms, kitchens, garages, and outdoor areas. Section 210.8 specifies the locations where GFCI protection is required. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, utility switching, and other events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance and at branch panels. Section 285 provides requirements for surge protection devices. Now let's delve deeper into specific scenarios. Consider a detached garage. If the detached garage is supplied by a feeder from the main dwelling, and the feeder includes an equipment grounding conductor, a grounding electrode system is generally required at the garage. This is because the garage is considered a separate structure and requires its own grounding electrode system to ensure safety. However, there are exceptions. If the garage is supplied by a single branch circuit, and that circuit is GFCI protected, a grounding electrode system may not be required at the garage. This exception is outlined in 250.32. The grounding electrode system at the detached garage typically consists of a ground rod or other approved grounding electrode. The grounding electrode conductor is connected to the ground bar in the garage panel, and the equipment grounding conductors of all circuits in the garage are also connected to the ground bar. Bonding is equally important in the detached garage. All metallic parts that are likely to become energized, such as metal conduit, metal enclosures, and metal water pipes, must be bonded together and connected to the ground bar. This ensures that all metallic parts are at the same electrical potential, minimizing the risk of electrical shock. Now, let's consider a farm panel. A farm panel is typically used to supply power to various agricultural equipment and buildings on a farm. The grounding and bonding requirements for a farm panel are similar to those for a detached garage. A grounding electrode system is generally required at the farm panel, consisting of a ground rod or other approved grounding electrode. The grounding electrode conductor is connected to the ground bar in the farm panel, and the equipment grounding conductors of all circuits supplied by the farm panel are also connected to the ground bar. Bonding is also essential at the farm panel. All metallic parts that are likely to become energized must be bonded together and connected to the ground bar. This includes metal conduit, metal enclosures, metal water pipes, and metal fencing. In some cases, it may be necessary to install multiple ground rods at the farm panel to achieve a low enough ground resistance. The NEC does not specify a maximum ground resistance value, but a ground resistance of 25 ohms or less is generally considered acceptable. Measuring ground resistance requires specialized equipment, such as a ground resistance tester. The tester injects a current into the ground and measures the voltage drop to determine the resistance. It is important to note that grounding and bonding requirements can vary depending on the specific location and the local electrical codes. It is always best to consult with a qualified electrician to ensure that the electrical system is installed in accordance with all applicable codes and regulations. Improper grounding and bonding can create a serious safety hazard, potentially leading to electrical shock, fire, and equipment damage. Therefore, it is crucial to pay close attention to these details and to ensure that the electrical system is properly grounded and bonded. In addition to the NEC requirements, there are other factors to consider when designing and installing a grounding and bonding system. For example, the type of soil can affect the effectiveness of a ground rod. Sandy soil is less conductive than clay soil, so a longer ground rod or multiple ground rods may be required in sandy soil. The presence of underground utilities can also affect the placement of ground rods. It is important to avoid installing ground rods near underground gas lines, water lines, or sewer lines. The size of the grounding and bonding conductors must be properly sized to handle the expected fault currents. Undersized conductors can overheat and melt, creating a fire hazard. The connections between grounding and bonding conductors must be properly made and protected from corrosion. Loose or corroded connections can increase resistance and reduce the effectiveness of the grounding and bonding system. Regular inspections of the grounding and bonding system are recommended to ensure that it is in good working order. Any damaged or corroded component should be replaced immediately. Grounding and bonding are not one-size-fits-all solutions. Each electrical system is unique and requires a tailored approach. A qualified electrician can assess the specific needs of the system and design a grounding and bonding system that meets all applicable codes and regulations. The NEC is updated every 3 years, so it is important to stay up to date on the latest requirements. Changes to the NEC can affect grounding and bonding requirements, so it is essential to be aware of these changes. Understanding the principles of grounding and bonding is essential for anyone working with electrical systems. Whether you are a homeowner, a contractor, or an electrician, a basic understanding of grounding and bonding can help you to stay safe and to ensure that the electrical system is properly installed and maintained. Remember, when working with electricity, safety is paramount. Always take the necessary precautions to protect yourself and others from electrical shock and fire. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work. In summary, grounding and bonding are essential for electrical safety. They provide a low-resistance path for fault currents to flow to earth, protecting people and equipment. The NEC outlines specific requirements for grounding and bonding, and it is important to follow these requirements carefully. If you have any questions about grounding and bonding, consult with a qualified electrician.